Okay, so here I am starting to put together a little MDF jig on top of the spoil board to attach the raw stock for this next milling operation. All of these first few videos in this series are just one quick project I put together on a Sunday afternoon to kind of demonstrate the process. So the idea here was to screw a separate piece of MDF down to the spoil board so I can mill a little pocket in there so my material will fit in. So I've already measured at this point the material that I'm planning on putting in, and this piece of MDF that goes on top should be able to accommodate that. So just drilling some clearance holes for these screws. These are just drywall screws. I put 1 5/8" screws, and I'm putting them towards the corners. So I'll end up modeling all of this in Fusion 360 or HSM Works or some other program, so I can make sure I'm not milling my screw heads off. This is probably overkill, but I wanted to kind of do some overkill just to demonstrate what kind of precision you can get if you want, and ways of kind of registering your workpiece. Things like this also work if you're flip milling and you have an odd-shaped piece that you want to locate somewhere on the bed. How are you going to pick a corner up off of like a figure 8 or something? So here I've skipped ahead a little bit, and I am now installing the collet. This has tripped a couple people up. If you install the collet into the collet retaining nut first, you can save yourself a lot of heartache by getting the collet jammed into the spindle taper. So I'll try that here. There's 2 tools, one wrench that holds the spindle in place so it's not rotating, and the other is just a little spanner wrench that allows you to tighten that collet nut down. So this is always kind of a tricky thing. I don't know that I know the best way to do it, but it's kind of like a 3-handed operation. I'll usually tighten it by hand and then use the spanner to finish it off. If you tighten it by hand, you can kind of get it in there so it doesn't fall out, and then you can do the final tighten. So it's important not to over tighten that as well, and that's a difficult thing to communicate. So if you've never done this before, it's maybe not the worst idea to ask someone who kind of knows roughly how tight it should be, and they can help you get that feel for it. Here I am beginning to pick up the surfaces on this little piece of MDF so I can have some sort of origin or coordinate system to work with. So the first thing that I wanted to do here is just pick up my Z. And so I'm demonstrating how you can do that with a tool in the spindle. And there's a million ways to do this. There's a million ways to pick up all of the different axes. But this is kind of a standard, simple way that it's often used to introduce people. So you can put a piece of paper underneath the end mill and inch it down 1/1000th of an inch at a time. You got to be really careful not to inch it down 1/8 of an inch at a time when you're this close to the material. That's pretty critical. But once you have it close, you're just waiting to get a little bit of resistance on that paper. And then once you do, you know you're on top of your workpiece. Maybe offset the thickness of the paper if you're really fussy about it, and you can measure that with calipers. Or you can just call it 0 and you're probably fine, because you're going to be a little bit above, if anything. Also with this MDF, there's enough variation in the thickness of the MDF bit. Certainly for milling your fixture, it really doesn't matter that much. But you'll get a feel for these kinds of things the more you do them. So here I think, yeah, I'm starting to feel a little resistance. And then you can hop over to the computer. Once you have that, once you're physically at that location, you can hop over to the computer and tell it, hey, I'm at this location, the z-axis. It's a little confusing actually, and it's actually caused, I think, some people some problems. You have your tool length and you have your Z location. So when you're programming, you need to make sure that the same tool that you taught the length with is being used. So tool 1, tool 2. In this case, I'm actually using no tool, if you look closely at Linux CNC. And that actually kind of tripped me up. So I actually had to go back and do a tool touch off. The next time I show you the screen, you should be able to see that. This is probably what explains the Z height jumping around on people. You program one path with tool 1 and the other path with tool 2. If it doesn't explicitly ask you to make sure tool 2 is in there, or even if it does, you might not know that you're, because Linux CNC behind the scenes is storing all of those tool heights. I may make a more in-depth video about that later. So here I'm picking up the edge in X, and it's kind of confusing here too because I'm on the back left corner. You probably want to do this all on the front left corner, which makes the most sense with the coordinate systems in your cam. I was doing this all without audio, so I'm drawing this out to make it really explicit. I've got a 1/2 inch shank diameter on my tool. That's what fits in the collet, and a 1/2 inch collet. And in my particular instance, I'm using actually a pretty big end mill for this machine anyways. It's a 9/16 end mill. I just happen to have a relatively fresh cheapo high-speed steel end mill liner. So I'm doing the math for you here to get the decimal conversion and drawing out, in case it's not perfectly clear, what you have to do to find the tool center point. So all of these coordinate systems are based on the center of your tool. They're not based on the edge. Or at least that's what will make the most sense if you're programming. So if I'm touching the edge of the board, I'm actually off the corner by -1/2 the tool diameter. Right, so my X position is going to be actually 9/32 of an inch. I put 0.281 to round up because 1/1000th of an inch is more than enough precision there. See, I'm still in the back, that top left corner. In the next video, I think you'll see kind of magically jump back down to the bottom left. So pay attention. Here I'm showing you how you touch that off again with the various different axes. You touch each axis off. And you can explicitly type in what coordinate you're at. And then you'll see there in the top left of the screen, the black part of the screen, where it thinks it is. Here I'm actually labeling the workpiece with the coordinate system in the bottom left. Not a bad idea to remind yourself sometimes. You can really put these coordinate systems wherever you want. They just need to be the same everywhere. They need to be the same in the real world as they are in your program when you're doing the programming. That's the critical thing. And when I get to doing the programming video, I'll make that more explicit too by showing you where I've put the coordinate system. So I think, yeah, here I'm just touching off another axis, putting in half the tool diameter. Oh. You can actually drive to this corner if you're somewhere else and you've input that corner as 0, 0 by typing G0, X0, Y0. That's a rapid move, so it can go fast if you don't have your speed override set, but it'll actually drive it. You do that into the MDI tab in Linux CNC. Here I'm just showing again, making it very explicit what's going on here. I have the center of the tool on the bottom left corner of that workpiece. That's my 0, 0. And I've chosen to have Z0 be the top of the workpiece, or the top of my jig that holds my workpiece. You can do whatever you want, you just need to make sure that it's the same in your program. If you're using 2D CAM software, sometimes they kind of constrain you. Okay, so here I'm trying to show how the tool offset works. So the idea is that this is tool 1 for my program, and I need to teach it the length of tool 1. So I actually have the G code loaded in this instance. I'll show you more about that later. And I'm telling it it's at 0, it's at the top of the piece. So you need to see that you're at 0, 0, 0 with that tool loaded. Otherwise you'll end up with a little surprise where potentially it's loading the length of a tool that you had in a previous program or something. And you need to check to make sure your G code is using the tool that you just taught. Okay, so now I am just showing a little video where I'm trying to run this program. And here, this might seem like the least important thing, but this is really kind of the most critical idea that you could take away from maybe the whole video series, which is start out really slow. You can move the rapids and the feeds way down to 0, so it's basically paused. And as the end mill is approaching your workpiece, you can just double check, triple check, and quadruple check that you're in the right spot, that your Z is correct. And as it starts to move in the XY plane, you're changing probably from a rapid to a feed move. So as you creep that feed rate up, you can start to see it cut. But you can really avoid pretty much any problem, or tell if your offsets are wrong, or you didn't set your Z right, or you programmed the coordinate system wrong. You can catch all of that, and you should. Whatever is going wrong, you should catch it. That should be your mantra. The only time you shouldn't check everything and run things slowly is if you've run it like 100 times and you're absolutely confident that it's been proofed out, that you have everything right, and you're just repeating something you've done a lot of times before. So you can see I'm cutting obscenely slow here. I'm just going to pocket this out, and then in the next video I'll show you how I can fit my piece into a little square that I've cut out so I can register things. That's it for this one.